All right, Stefan's here so we can get started. All right, so I want to make a mention of where we were last time. I put a note on the piazza about something I was thinking about when I was on my way to Indiana. I realized that there was a mysterious lemma last Wednesday that I think didn't come across very clearly. So let me give you a sketch of what's going on. I found a different way to think about it. So the idea was, so this is from last time, is we suppose that we have a quasi-inverse for f. So a quasi-inverse for f, I'll call it G naught, alpha naught, and beta naught, is a proof that f has a quasi-inverse. And remember what that means is where f is some mapping from A to B. So what that means is we have a mapping in the opposite direction, and we have these, you can write these in, well, the easiest way to do this is to say that G naught composed with F is the identity, and that would be on A, and beta naught will say that F composed with G naught is the identity on B. Okay, so that's the data that we have in a quasi-inverse. And so we have that situation. And then the claim that is there is that the type of quasi-inverses of F is equivalent to the type X in A, X equals X in A. Okay, that was what we set up. And people, it was a little mysterious, like why we were doing this. So I want to point out two things about it, and then it'll make it much clearer, I hope. Made it much clearer to me. So this is equivalent to saying, in the presence of function extensionality, that the identity is equal in A arrow A to the identity. So that's a better way to notate that, to be honest. But the reason this notation is somehow, I mean, they're equivalent, but the reason this notation is maybe a little more informative is because the way we're going to exploit this fact in a moment is by exhibiting a space A and a base point X in A whose loop space is non-trivial. And this is the loop space. So this is also known as, this is really the product of the loop space of A based at X. And so that's just another notation for this. Okay, so this is called the loop space. It's a nice notation with omega because it looks like a loop. Okay, so it's a loop space. And so the idea is that there exists types A with a non-trivial loop space at some base point. And that will be exploited momentarily. So that's the reason. So the reason for writing this, which is equivalently written like that, that's just the definition of omega, okay, is to emphasize that aspect of it. But for the purposes of this proof, it's a little easier to remember that this really means that. Okay? Okay, so now let's look at what is quasi-inverse of F. Well, this is sigma G in B arrow A, sigma alpha in G composed with F is the identity, sigma beta, which is F composed with G, is the identity. Okay, dot one, let's say, if you, I want to write it as the three sigmas like that. Okay, because the elements of the, okay, officially I should have the null tuple in here. Well, you'll forgive me my nil. Okay, so this is the type of quasi-inverses. Okay, that's just expanding out the definition. So here's the point. The point is, the remark is that the 2/3 of this, namely sigma G, B, and A, with sigma beta F composed with G is the identity, one, is contractible with center G naught, beta naught. This is the important point, okay? So remember what contractible means. Remember that the word contractible should be, you remember that means exists unique. So in other words, what this is saying is, since F has a quasi-inverse, this says F has exactly one right inverse. The statement that type is contractible is saying it's inhabited, but that's given up here. F has a right inverse. And, okay, if you give me any other thing, which is in this type, it's equal to that center of contraction. So let's consider, just to show on the side, let's consider G1, B1 also in that type, sigma B and A, sigma beta F. Consider another right inverse. Okay, consider another right inverse. Okay, so what I need to show is that, in particular, I need to show two things. G1 is equal to G0 in B arrow A. And then I need to show that beta 0 is equal to beta 1. Let's say, call this a path P. So we need something here over P. In other words, the transport of this guy by this proof will be equal to beta 1. So those are the two parts. Because it's elements of a dependent sigma, of a sigma type. And so remember, the equality in the sigma type means the first components are equal, give me a path P, and the second components are equal over P. They're correlated by P, words like that. And this is in an identity type. Okay, so what goes up here is an identity type. Okay, so it's F, this is in the family in question is F composed with blank equals the identity. Okay, so that's what we're doing. So we have to do that. So let's look at this guy. Okay, we want to show that G1 is equal to G0. Okay, so what do we know? What do we know? So the idea is that we know that, yes. So we know that, I think it goes like this. So we have another outright. So we have G1 is in here. And we know that G1 is a right inverse. So we know that F composed with G1 is equal to the identity of the appropriate type. Okay, this we know because we're given this element. Okay, so this is by beta 1. Is the reason why that holds. Okay, right? So we agree because beta 1 says I've got that G1 is a right inverse to F. So now what I do is I compose both sides. Okay, with G0. So that means G0 composed with F composed with G1 is equal to G0. Using a little bit, this is with composition. And I'm actually going to reassociate that, and I'm actually going to cancel. This is really G0 composed with the identity. So modulo a little messing around, okay? But now, by alpha naught, which I have over here, this is the identity, right? Which is over here. So therefore, I get that G1 is equal to G0. And now if you look at the path that I've computed here, you have to write it down, and you do this calculation, and you look at what is transport inside the identity type. It's just composition post-composition. Okay? I gave you that before, so you can check this, that this will be the case. So that shows that this type is contractible. So now what do we know? So now what do we know is that we have sigma B and A. So this is the type of quasi-inverses, right? Alpha, I'm writing it again because I want to do it pictorially. And in fact, let me swap the order. Okay, so quasi-inverse, the type of quasi-inverses, that's this thing, is equivalent to, let me just swap the order because it's convenient for, so I have swapped the order. There we go. And this will be G composed with F as the identity. Okay, so I just swapped the order there. And so what we've shown is that this piece of it is contractible. Okay? This piece of it is contractible. So this is equivalent to 1. okay? That's what we're doing. In the presence of the fact that we have this data, okay? So that's what is happening here. And so what we're, so what we're left with, okay, with the quasi-inverse is we've gotten rid of that. So what we're left with is, when we're done, what we're left with is showing that what we have is that the thing we're left to show is that the type G naught equals, G naught composed with, is that the thing that's contractible? Yeah, that's the thing that's contractible, right? Yeah, so I need to know that the type G naught composed with F is equal to the identity. That's all that's left, okay, in the idea of, because this is contractible with a particular element, okay, which has G naught, which has this as center, okay? So what you can then end up saying is that the quasi-inverse is just that. In other words, if I look at the, oops, not G-inverse, quasi-inverse, that the data that constitutes F being a quasi-inverse really just amounts to showing, well, there exists a G naught such that G naught composed with F is the identity. And there's at most one. So we can look at it like that. And now, if you take this guy and symmetrize it, you'll see that this is ID equals G naught composed with F. And then if I do transitivity, I get this is ID is equal to ID. See, I can just take this fact, right, swap it around by symmetry. So take a path here, swap it around, take its inverse, compose it, you get ID equals ID. And then backward, if you take something, so that's what we have here. We need to show that, so this is the thing that I previously remarked we want to do. This is the target that we want. And then the other way around, if you have such a thing, you can just precompose over here and get the G naught composed with F is equal to the identity. And that's what you're left with. So the idea is that once you know that F has a quasi-inverse, then 2/3 of the data associated with being a quasi-inverse is cancelable because it's contractible, because there's a unique one. So once you know you have a right inverse, then the type of all the possible right inverses is contractible because you've got one. Okay, that's what this is saying. So the only thing you're left with is one additional piece of data. And then you can show that that additional piece of data, which is remaining around, that is what quasi-inverse is. And that is easily shown to be equivalent to the identity equals the identity, which is the product of all the loop spaces. And then we applied the lemma by saying, okay, so at that point we know that quasi-inverse of F is equivalent to pi x, the loop space of A at x, right? Like that. Then we appeal to another lemma, which is there exists a type with a non-trivial loop space at a certain base point. So an example would be, so an instance of this guy was going to be the loop space of S1 at base, okay? Or actually, as I mentioned, you can, and if I want to make that a set, I can just do a zero truncation of that and look at its fundamental group. So we can, the zero truncation of that is by definition the fundamental group pi1 of S1. And we know that that's Z. So this is non-trivial. So we have it, it's not a proposition, okay? So, so therefore we can conclude that this is not necessarily a prop because there exists an element of this for which this is not a prop, okay, like that one. And therefore Q_inv of F, which is the product of all of them, is not going to be a prop. And so, and that we didn't actually prove. In the book, there's because of the order of development that is required, they do an ad hoc proof of a particular space. They didn't use a so-called natural one like pi1 of S1. They contrived one. and then later there's a very general construction called the Eilenberg-Moore spaces, where you can make a space whose loop space is whatever group you want. So if I want that group, the additive group, let's say, then I can make a space whose fundamental group is that. So the point is, this is wildly not. This is never a prop, basically. You can go crazy. You can make it whatever you want. So this is as complicated as you like. Okay, over here. This should have said pi x in A. Da-da-da. Okay, and you can make that as nasty as you like. But because of the order of development of ideas in the book, it wasn't quite available yet. So I'll just forward reference a lemma that says, you can make all sorts of crazy loop spaces, and then you end up showing that quasi-inverse is not a prop. And now what's nice is if you look at the notion of bi-inverse of F, remember what is that defined to be? That says you have, let me just call it R and L just to remind us. You have a right inverse, so that F composed with R is the identity, and you have a left inverse such that B to A, that's the L composed with F is the identity. That's the definition of a bi-inverse for F. And so in the case of a bi-inverse for F, you can do the same argument. This is going to be contractible because there's at most one right, given that F has a quasi-inverse, then, given that this is inhabited in particular. So if it's true, then this is contractible and that's contractible. So the expression has at most one proof. So if it's true, it can be true in at most one way, because both of these pieces are contractible, okay? And therefore the whole thing is contractible given that it's true. So that's what we're saying over here. Given that it's true that we have a quasi-inverse, well, we might have liked quasi-inverse of F to be contractible, but the argument is it's not. And the reason it's not, which is, I don't know any better way to say it, is it doesn't quite have enough data. It has one mapping which has to be both a left and a right inverse. And so to say we use it up in canceling it out and we're left over with some additional data. Okay? So it ends up not being an H prop. Whereas if I let you have seemingly separate left and right inverses here, okay, like that, then I can cancel both of them given that it's true, and then it expresses an H prop. And then there's some further discussion that relates bi-inverse to half-adjoint equivalents of F. Those end up being equivalent, and that ends up being equivalent to, what did I call it, contractible fibers? What was the, I forgot what notation I used. What did I call it?
You just wrote is contract.
I didn't give it a name?
You wrote is contra.
Okay, contractible F, okay. Okay, so this says the homotopy fibers are contractible. And then what I was trying to train you to do at the end last time was to read are contractible in terms of exists unique. So then the homotopy fibers are, right? So we're saying for every for every y in B, okay, we said is contractible, just to remind you, the fiber of F over Y. So that was this picture. You pick a Y here, you look at the fiber over F, and you say for every such Y, and there's another Y prime, that this is contractible. But for that to be contractible means that there's a unique element here up to homotopy. That is, these are all equal by a higher dimensional path. So for every one of these, there's exactly one of these. And every one of these, there's exactly one of these. And of course, you have a map F going downward. So for every one of these, there's exactly one here. That's because it's a map. But it's also the case that wherever it landed, and not even, it's going to land everywhere, because pick any point you have here, there actually is going to be an inhabited fiber. So we know that it's, so to speak, onto. And then every single thing is, these are all equal, these are contractible. So it's one-to-one and onto up to higher homotopy. And so you think, oh, well, duh, okay. So this is essentially saying F is bijective up to homotopy. That's what is really being said there. And so in the book, there's a relation, these are all discussed, these are all shown to be equivalent. And off the top of my head, I don't remember exactly what is the most optimal order in which to show that these equivalences hold. They're in the book, I didn't really memorize them. So, but you can look at it. So I think with like these a little additional hints, I think the whole thing will seem a little clearer, and I hope. And the proof that's in the book of this fact over here, I think is maximally obtuse. I mean, all the pieces are there, but it goes through some crazy thing with univalence and a path induction and stuff, and you don't really need all that as far as I can tell. So anyway, the main point is Q inverse of F has this characteristic that 2/3 of it is cancelable, but not all of it when it holds. Whereas by inverse, it's all cancelable when it holds. And then by various arguments, this is equivalent to that is equivalent to that. And so that's why. So that's the idea. So in the end, it was just a way of saying that it's reasonable to speak of by inverse of F, for example, is true, because you're saying it has an inhabitant, and there's no point in distinguishing which inhabitant because there's at most one. Okay? And that way you're justified in speaking of it as being true, and nothing that comes afterwards could depend on what the evidence is for it being true, at least up to higher homotopy, because there's at most one. So as soon as you say there is one, anything you could have written down is as good as anything else. So you're allowed to say by inverse is true. So when it's true, or you could say it has at most one proof, or another way of saying it is, when it holds, it has exactly one proof. I mean, it's the same thing, right? You could phrase that statement either way, okay? Yeah.
Why is that so important?
I think the significance of that is inflated. If you ask my opinion, okay? And the reason, I think there are two reasons why. It doesn't say anything about the definitional equality. So we know that the definitional equality, the definitional properties, if I have P, which is a particular proof of by inverse of F, P can be definitionally equal to some P prime, and that may matter for even for the statement of a subsequent theorem to even be syntactically well formed. So the unicity up to higher homotopy helps you not one bit with this fact. Okay, so this is a fundamental problem. Okay, and this fact doesn't help. However, if you're always working, if you somehow arrange things so that you never export definitional properties, I'm not sure how you do that, because you saw me doing arguments where I cared. So like here I'm a little on thin ice. I don't know what works or what doesn't work. We have to figure this out. But if you were in the case that you only ever cared about this thing up to homotopy, then the point would simply be, I can simplify my proofs. I only just have to write underscore. I don't give a damn what it is, because its existence is all I care about, and any other one is equal to any other. And as long as I'm only working up to higher homotopy, I'm fine. Okay, so that's the reason. It basically comes down to, I can simplify certain kinds of arguments by saying something is true without caring about the reason why it's true. Whereas, like, just to be silly about it, it's not really very helpful to point out that NAD is true. It's very unlikely in the remaining of your argument that that mere fact alone is going to be of use to you, and you don't care what number it is that validates it. Okay, I mean, I'm being a little sarcastic, but so you tend not to say that, because that's a set, that's not a proposition. But when it's a prop, then there's no useful, so to speak, there's no useful data, at least up to higher homotopy. And so that's why. However, I said to you before, this whole idea of using the word prop, part of it is just colliding traditions, okay? But the whole idea of using the word prop for talking about types that have at most one element, or have one element when they're inhabited, whatever you like to say, okay? In calling those props, okay, one is you can just say it's a tradition and we just have to meld traditions, and that's fine, okay? But I think it's a holdover from classical thinking anyway. Okay, that somehow some people, depending on where they come from, like to think of propositions as things that have at most one proof. But the entire point of constructivism from day one, from Brouwer's first writings, is that there is not one proof, and the structure of that proof matters. That is the absolute heart of Brouwer's program of constructivism. So it's a real terminological clash. So you could say, well, maybe we should call these things sub-singletons. And it's a bit of a mouthful. Nobody thought of a better word that I know of, okay? So everywhere I said prop, I could have said sub-singleton. But really the motivation, you could call it sub-singleton, but I think the inner motivation is to want to be able to write this. And I think the insistence on writing this is a holdover from classical logic, okay? That if you're in constructive setting, you want to be doing proof-relevant math, and you shouldn't be doing that anyway. That's personal opinion, okay? So heavy weather is made of this. There's a whole chapter in there about this business, and to be honest, I have not come to appreciate that point. Okay? In fact, you could say, my impression is it's the opposite of what is the right point to be making, but people I respect think otherwise, so I imagine that I have something to learn. But anyway, as far as I know, this is the story, okay? So I just wanted to clarify that. So when I was on the plane to Indiana, I thought, okay, that really was not very clear, was it? So I tried to work out a better way to think about it. So you can work that out on yourself to get all the details down there, but that's the gist of it. Okay, so now for something completely different. So now I want to talk about inductive types. And what I'm going to do is I'm going to back us up now to where we were very much in the beginning of the semester and then go forward again. Okay, so you remember that in the very beginning of the semester I started out with simple types in order to talk about proof relevance in isolation from the idea of dependent types. That was the scenario. Okay, so what I want to do is I want to go back to that spot, and then I want to once again go forward, but I want to go back to it first in the setting of inductive types. So let's look at, all right, so this is the plan. And the lecture plan I have in mind has some informality to it. In other words, I'm going to gloss over a few points so that later when I come back and talk about them more precisely in the context of homotopy type theory, you will have already gotten the main ideas already down, and then you'll be able to follow better the technicalities. Okay? So that's my plan. All right? So just so you know. Okay, so everything I'm going to say here is there's a certain spots where I'll point out what's going on. Okay. So let's go back and reconsider. So let's reconsider NAT, the type NAT in simple types so we're going back now to week 1 of the semester. So what I did when I did week 1 of the semester, when I defined ITT, apart from NAT, I did include NAT, but I left out deliberately the general story of inductive types, which is now what I'm going to tell. And the way I'm going to tell that story is I'm going to go back to what we did on NAT and reorganize it and look at it in a slightly different way, which will position us for being able to say things more generally. Okay, so that's what I want to do. And there's some stuff that I want you to know, so I'm going to teach about that as well anyway. So reconsider NAT. So we're going back in time now, so it's like everything, we can kind of relax a little bit. So remember that we had introductory rules. So we said 0 is a NAT. And we said, if M is a NAT, then successor of M is a NAT. Okay, so those were the introduction rules. And then the elimination rule was the recursor. which is, we said if M is a nat, and I think I might have called it naught is A, let's call it, and assuming X is in A, M1 is in A, then we said that the recursor at A of M naught X M1 is in A, and it had some definitional equivalences, okay? And the betas were rec A, 0, this is all just, I'm reminding you, you've written this stuff before, so I'm just reminding you because I want to have it on the board for discussion. And then we said something like successor of M naught X M1 is a substitution of, you make the recursive call on the predecessor. It gets a little heavy, I'm sorry. And you put that in for M1, and that was this would also be an A. Okay, so those were the beta-like rules, you'll recall those. And then the eta rule we talked about, what it would be is to say that if I have any other map, so if I know that 0 for x n is M0, and if I know uniformly in Z, in nat, if I know that plugging in successor of Z for x in n is the result of plugging in n, Z for xn, I could have called it, I could have used my letters a little differently, but Z for xn for x in n, then what we know is, one way to say it is, for any Z in nat, or I'll call it x in nat, okay, n is the recursor. I'll have to double check that I didn't make a mistake here. Okay, so this should have said M1 over here, and then I think I think I said it right. Okay, so those were the rules that we considered. At some point we said we're not going to consider this as a principle of definitional equality, but now I want to discuss all of that. That's part of what I want to do here, okay? So another way of organizing like these things, there's a couple of different ways of organizing these things. But one way to organize these things is I could have said the following thing. I could have said, in the empty context, 0 is nat. And I could have said, given x in nat, successor of x is nat. So this is what I could have said on the introduction. So this is the elimination, by the way. Okay, I could have said those two things. Why? Because of a general principle of weakening, I can throw in a gamma. I need some way of saying this. So depending exactly on how I organize the theory, you could, the formal rules, and I've been a little loose about exactly what are the formal rules. But what I want to say is, when the system is suitably set up, another way to formulate it is, you say 0 is in nat, and given x in nat, successor of x is nat. And then it follows that I could put, or you have a rule that allows it, that I can drop in a gamma here, and I can drop in a gamma here, and then if I have gamma proves m in nat, then I can substitute and get the rule that I described over here. Okay? So what I'm saying is, this information is equivalent to that information in a suitably set up theory. Okay? Do you see what I mean? So the core of the information is just this. All right? So that's what is going on. And in fact, I could even do it if I didn't mind using the arrow in order to define the nat. So the nice thing is this is all orthogonal. Like I can define what natural numbers are without assuming there exists any other type constructors in the world. But if I was willing to be a little sloppy and ugly in a certain way and take advantage of other type constructors, I could also have said 0 is a function from 1 to nat. And for that matter, I could just abbreviate that as nat, but I'll write it like that. And I could just as well have said successor is a function from nat to nat. And then in a suitably set up theory, I can derive these rules from these two constants. So these are two ways of writing the same thing. The difference is that what I'm doing here is, this is a mapping, right? And this is a mapping, whereas this is an element of a function type of the exponential. All right, x, and here is an element of the exponential. So there's a correspondence between this successor and that one and this one and back and forth, but they're not really the same thing. But there are different ways of writing them down. In the sort of, seat of the pants programming languages world where people don't really know any theory, they get all these things all screwed up and they start talking about special forms and all sorts of crazy ass stuff. And basically they don't know what they're talking about. So but I want to draw out this distinction for this purpose because I have a pedagogical reason to want to do this. So, okay, so whichever way you like it, you could think of them as maps or you can think of them as elements of function types like that. And the same thing is going to happen over here, okay? One of the things I could have done here is I could have written the rule like this, kind of equivalently, and it'll end up being helpful to do this. I'll leave out this guy, m nat in the beginning, and what I'll do is I'll say, if you give me data like this, okay, and you give me data like this, where is it, x and a, then I will give you, this is another way of notating everything. I'll think of that as a function. Well, one way to think of it is as a function, or another thing is as a mapping. So given x in nat, let's even write it, let me write it z just to be like, I don't have to, but I'll just do it. I'll re-parenthesize it, and then this will be a. Okay, so now what we're saying is, if you think of it like this, what we're saying is this guy, I wrote it with a notation that kind of looks like application for a reason, because I'm being deliberately ambiguous between that and saying that it's an element of the exponential. So I could say this is an element of the exponential nat arrow a, and then it would make sense to write applied to z. So there's a little like notational fiddles that one can do, okay? But it turns out to be helpful to do that, okay? So that's the idea. And why, let's look at this one for a minute. Modulo the fact that I re-bracketed things. If I know that m is in nat, then by substitution I can plug it in for z and I can recover the information on the left-hand side, okay? So that's why this is saying the same thing as that. On the other hand, if z really is around, then I can, if there really is a z here, then I can weaken all of these to put the z there, and then the m becomes the z, and then I get the z as a special case. So they're completely the same. Assuming you've got the right ambient infrastructure, because the exact choice of rules can be made in different ways to make certain things more easy and not. And I didn't want to get into all the minutiae of proof theory, so I've been a little loose about it, and I'm going to continue to be a little bit loose about it. So I want to just give you like that flavor, okay? So the way you could look at this, right, is, and in fact, if I want to suppress the gammas here, what I'm saying is, or if I want to look at it like this, or I can look at it like this, I can say m naught is a mapping from gamma to a, m1 is a mapping from gamma cross a to a, okay? And therefore, this rec is a mapping from gamma cross nat to a. That's what we're saying here, all right? Okay, so that's like the first like little technical maneuver I need to make, okay, in order to say something about this is, I'm just reminding us what we're doing, and I'm in the middle of doing a reorganization. Some of you no doubt know where I'm heading with this, but I'm not assuming that everyone does, so I want to go through this. Now, I want to mention, by the way, that this thing is an induction principle, right? And in fact, in the book, this rule is stated in a slightly different way. Instead of saying, these conditions tell me that n is equivalent to the recursor, they instead say, if you have two functions which satisfy these conditions, then those two functions are equal to each other. In particular, it would be equal to the recursor. But it's the same thing, because if I want to show that two functions are equal in this manner, then I can show that they're both equal to a common recursor, and then I'm done. If, on the other hand, I take as a rule that says two functions are equal when they behave equally in this manner, then they're equal, then in particular I can plug in one of them to be the recursor and derive this rule. So it's kind of like you can do it either way, all right? Okay, so what's happening is if you don't understand everything I just said, you're going to have to work that out for yourself and just read the things in the book. So this is, remember, the unicity. This is Genson's unicity principle, and this is the inversion principle. Okay. So the inversion principle is, well, we're going to see, it's a commutative diagram, and the unicity principle is a uniqueness thing. This is expressing there exists a map from Nat to A that satisfies these equations, and this is saying if you have any other mapping from Nat to A that satisfies these equations, then it is the recursor. So it's unique. So now let's look at how we would really write that out sort of diagrammatically. So I can rewrite this information in a slightly different way. What I can do is I can say this: if you give me Z in 1 plus Nat, then there's some data which is in Nat. And what is that data? So what I can do is I can write it down. This I'll use in my notation for case analysis. Underscore dot 0, and what did I call it? X? Yep. X dot successor of X. If I need a little bit of room. This is my case analysis, and if I want to make it explicit, applied to Z is in Nat. So this is just a notation for case. I don't remember what I wrote before. Case, I don't care what this is because it's in 1, 0. And here I write successor of X. Whoops. That's what I mean by that. So in a slightly more abbreviated notation, I can write this as 0. Don't bother with the underscore because I don't care. This is a little bit of abuse. But with an abusive notation, I could write it like that. I really should have the Z here, so I can do that is Z. Okay, so I can write it like that. That's a slightly, it's just helpful for me to have a simpler, a lighter weight notation for the case analysis for what I'm going to do next. So this is another way of summarizing this. Because why? The principle of case analysis tells us that if I have, if you have 0 in successor, I can make a mapping from 1 plus Nat to Nat. And if you make a mapping from 1 plus Nat to Nat, 0 consists of plugging in left of the null tuple here, and then using that. And then you have a Nat to Nat, so if I plug in right of M, then whatever this mapping is will be the successor that gives me a successor of M. Okay? So they go the same way, right? So if I were to have Z in 1 plus Nat, arrow, and let's just give it a name, S, okay, is Nat, yeah, let me call it N, okay, is in Nat. Suppose you give me one of those things, then what I can do is I can just say, well, what 0 is N, well, you have to plug it in. So N is in left of the null tuple for Z in N, and given X in Nat, the successor of x is by definition in right of x for z in n. In other words, if you give me any map like this, then that's the way I'm going to regard it as giving me 0 and successor, is in this manner. Okay? So that's a way of doing it. And this could be notated if I want n0 and n1 of x. We could write it like that. Okay? And then you can check that these things up to an eta equivalence, the definitional equivalences for sums, let's assume we have them all, the ones we discussed earlier, then these are just two different ways of presenting the same information. Okay. So writing it like this, what we do is we say we have 1 plus nat, and we have nat, and the mapping here with a slight abuse of notation is the case analysis 0 successor. Okay? So this mapping is called a nat algebra. That is, any mapping from 1 plus s, 1 plus nat to nat will be called a nat algebra. Let me call it alpha, okay, to remind you that it's an algebra. So any mapping from 1 plus nat to nat, any mapping from 1 plus nat to nat is going to be called a nat algebra, just by definition. The reason it's called a nat algebra is it's the structural part of what are the natural numbers. The natural numbers are a mathematical structure that has a 0 and a successor. And then it has a spec for how they behave. But the raw data, it's like saying a group is a set together with a unit element and a multiplication and an inverse. And then there's going to be some laws that it has to satisfy. That's what I'm going to get to in a second, okay? So it's not any nat algebra, but I'll explain. So the nat algebra is the raw structure, okay? Again, I'm hoping I'm not boring you. I'm trying to teach this as if you don't know these things. So, okay, I'm not positive that that's true for everyone. Okay, so what I'm doing is we'll call that's a nat algebra, okay? So in general, a nat algebra is a mapping from 1 plus nat to nat. If you have a nat algebra, you have naturally associated with it alpha 0, which is in nat, well, really 1 arrow nat, as I've defined it, and alpha 1 of x, okay, which is a nat, well, alpha 1, let's just say, is a map from nat to nat. You can write it like that. Okay, that's associated with it because you plug in left of null tuple here, that's your alpha naught, and that's a nat, and you plug in right of some number, and that's a nat, and we'll think of that as like the successor. So this can be thought of as the basis or the pseudo 0. In other words, given any nat algebra, there's no reason to think it's that particular one. So it has a 0, a pretend 0, which is alpha naught, which we normally call the basis. And this is the inductive step, which is a pretend successor. Okay, that's like maybe one way of saying it. Okay, but all right, we'll just leave it like that. Okay. So, right. And more generally, yes, this is what I forgot to say. I made a little mistake. More generally, that's a particular nat algebra that we have here. More generally, a nat algebra is an object A or a type A together with a map from 1 plus A to A. And so then what I said a moment ago makes sense. I shouldn't have written nat there before. What makes it a nat algebra is that it's 1 plus A to A, not that it's 1 plus nat to nat. That was 1 plus nat to nat is a perfectly good case of a nat algebra. This is a nat algebra. But in general, a nat algebra, is for any A, a map from 1 plus A to A. The key thing being the 1 plus A, okay? The pattern 1 plus A to A is what we're capturing here. So now back to what I said. This is our pseudo 0. It's the base case. And because we're giving nat structure to A. You see what I mean? So it has a 0 and it has a successor. Okay, which is otherwise known as the basis in the inductive step. Okay, so that's what a nat algebra is. And I'm going to come back to that picture in a minute. Now there's a notion of a morphism of a nat algebra because there's a category of nat algebras. So the nat algebra category is given by the following idea. If I have two NAT algebras, A and B, what is a mapping between NAT algebras? This is a thing, that's a thing. I want to say, what is a mapping between these things? Because I'm going to set up a category, okay? So a mapping between these things is a function, let's call it h, okay? And we'll call this 1 plus h, okay? And such that this diagram commutes. So this is what is called a NAT homomorphism. So a NAT homomorphism is a map H from A to B between these two NAT algebras such that this diagram commutes. And let's remind ourselves, what is 1 plus H? So 1 plus H goes from 1 plus A to 1 plus B. And what map is it? Well, what it does is it case analyzes its input. If it's 1, then it yields 1. It yields the null tuple. And if it's in A, let's call it little a, then it does in left of the null tuple. Then it does in right of H of A. That's the mapping. So this is what 1 plus H is by definition. So it means case analyze here, the 1 goes to the 1, there's nothing to do. There's a unique map into 1, so you don't have any choice here. I mean, you have a choice to send it left or right, but by definition it sends it left, and then once it decides to send it left, there's nothing to do. And then it takes the thing on the right, and by definition it's going to send the thing on the right to the thing on the right. And so how does it do that? It sends it to the right with H of A. Okay? So that's just by definition, okay? That's what that is. So this is a NAT homomorphism. And then you can define what are identities and what is compositions, and you check that they have the unit laws and associativity laws so that I really am talking about a category. So this is the category of NAT algebras. Let's write it like that. So the important point is a morphism of NAT algebras is a NAT homomorphism by definition. NAT homomorphism equals morphism of NAT algebras. You can probably already guess that I'm going to generalize the hell out of this because NAT is being used here for illustrative purposes. So at some point I'm going to make it unrecognizably abstract. But let's do the concrete case first. Okay. So that's the category here. So what does that mean? So back to the chase here. So this is a particular object in the category of NAT algebras. Okay? And the claim is that this is not any old object in the categories of NAT algebras, but that this is in fact the initial object in the category of NAT algebras. In other words, let's just call it initial object in the category of NAT algebras is called an initial algebra. But what is an initial object in a category? It's an object for which there's a unique map to every other one. So it's often notated 0 because think of it as a type. The empty type is the type that has a unique map to everything else, abort. Okay? Okay, but in general, an initial object in a category is one that has a unique map to everything else. The unique is going to matter a lot momentarily. So I'm going to claim that, given the rules that I've written down so far, that these rules induce, okay, the structure I'm describing in such a way that this is an initial algebra. So what does it mean to be an initial algebra? It means that if you give me any other algebra, like this, there's going to be a unique NAT homomorphism from left to right. Okay? So what is that? So in other words, that's a unique thing here, bang, such that 1 plus bang, that this diagram commutes. Okay, that's what we're saying, that this is unique. Okay, what is bang? By definition, what is bang here? It's the recursor. It's rec A, and I'm going to write it in a slightly different notation. I'm going to write it as, so this, I can just write alpha here. That would be a way of saying it. Rec A of alpha. Okay? And the important thing is that the uniqueness of this, in other words, you got to get the quantifier structure. I noticed from my office hours that some people are having trouble with this. These category theoretic diagrams have a, for lack of a better way of saying it, a temporal ordering or a quantifier prefix. So what I'm saying is, you know, there exists a thing, which is this zero successor, such that for every other thing, alpha, there exists a unique thing that has some properties. In other words, I just want to get the quantifier structure down. There exists something, that's that part, such that for any one of these, this is uniquely determined as a function of this. So being uniquely determined, given alpha being uniquely determined, means that this bang is a function of alpha. So I'll write it like that. Okay? That's the guy it determines it's a function of alpha, such that this diagram commutes. Okay. So now, like, this notation is a little, like, what I'm doing is, I'm doing the same thing I did here. I'm doing it with the recursor notation. So what I'm doing is, I'm packaging this up. I can write it as rec A, and then there are different ways of writing this, but the map in question is, well, with slight abuse of notation, it's this case analysis. Okay? Because this alpha can be thought of as alpha 0, alpha 1, in the way in which I described it over here. Okay? Because this alpha, up to some eta expansion, all right, can be thought of as a case analysis that gives you the answer on the basis of no data, and then gives you the answer on the basis of a previous answer. So to get this correct, this would be type 1 arrow A, and this would be type A arrow A. And then we're doing a case analysis. We're doing a case analysis to get this map. I'm slightly abusing notation, right? It really should be underscore dot A naught and all that business, right? But I'm slightly abusing the notation, okay? Because I'm being sloppy about elements of a function type versus mappings in order to make the notation work out smoothly. So I said to you, I'm going to do this with a slight degree of informality in order to give you the main ideas. So alpha can be thought of as having this form, okay? So that's true, and so that's what we're doing over here. So in the particular case, so this would be my alpha, okay, that's going on here. Because this information together is determining a map. If you look at it, it's essentially a map from 1 plus A arrow A. Okay, that's essentially what is going on here. Okay, because it gives me an A out of 1, out of nothing, and it gives me an A out of A, okay? The gamma's going along for the ride. If you want to really get this part of it right, there's some implicit applications of the Yoneda lemma in all of this, but I'm like glossing over that in a way that I hope will be intuitive at the board, okay? All right, so so that's the intuition about what I'm doing. So that's what I mean by this. So this is equivalently that case analysis, and then it's frequently common to just then drop the curly braces and put alpha naught semicolon alpha 1 here, where it's an implied case analysis on that. Okay? That's a way of thinking about it. Okay? That's just like the notational conventions. Okay, and now if we work out what the commutation of this is beta. All the beta rules are commute, because what it's saying is, if I run the recursor, if I take an input and branch on whether I'm going to emit either 0 or a successor, and then run the recursor on it, then what's going to happen is, it's going to, if it's 0, then I'm going to come up with this guy followed by alpha, and if you do the calculation, which I won't do at the board, you'll get alpha naught. And if you do the successor of some x and feed that to the recursor, then this is saying that you get the equation, the second equation that's over in the far left board, which is going to be alpha 1. Okay, that's what's going to happen there. Okay, composed with bang. In other words, alpha 1 of bang. Okay, so it'll end up saying, you know, yeah, that's what it'll end up saying. So you can check. So this you should check. Okay, I won't write it all. I won't write it all out at the board. Okay, but you should check that. So the mere commutation of that diagram is exactly the beta rules. So what is the eta rules? Well, the eta rules say if you gave me any other mapping, let's call it R here, which acts like the recursor, meaning that on 0 it is alpha naught, and on successor it's alpha 1. That's what I wrote on the bottom left board there, using substitution instead of composition. Then R is equal to bang, which is what I wrote on the bottom of that line over there. Okay? So the fact that I wrote bang for that thing to emphasize that it's unique as a function of alpha, which means if you gave me any other one that makes the diagram commute, then it's equal to that. So what's going to happen in the type theory, and I'll just start saying this right now. You notice I started being a little sloppy about my equal signs. The reason is that in the type theory, this unicity is going to be witnessed by a higher cell. This is going to be unique up to higher homotopy. Okay, that's one important fact. For the natural numbers, okay, these commute on the nose up definitionally, okay, for the natural numbers built into the type theory. However, what I'm going to do next time is I'm going to obtain the natural numbers as an example of something much more general, which gives us initial algebras for what are called a broad class of functors called the polynomial functors. And then this will only commute up to higher homotopy itself. This will also be witnessed by a cell. Okay, so this is part of what I'm saying, that this lecture is motivational, because I've been a little loose about what I mean by equality, and the whole point will be that when I analyze it in terms of type theory, then we have to be quite careful about what we mean by equality. Okay? And in fact, it's a little unsatisfactory in the analysis in type theory, because it ends up, when done in the full generality that I just indicated, everything becomes a propositional equality. You don't get any computational behavior at all out of the recursor when defined via the general mechanism. That's like, from a computer science point of view, that's a little unsettling. I haven't yet decided that I like that. Okay, so that's what's happening there. Okay, so now I wanted to say something else. All right, so are you with me so far? Are we? Okay, so we did a reorganization. I asked you to do these things. Okay, so then I did that, and I did that. Okay, so now the next thing is important, which I'll erase over here. There's two informal things I want to do next in order to set up the main ideas that are going to inform what we do more formally inside of the type theory. Okay, so there's first thing I want to do is something called Lambek's lemma. Oh yeah, but before I do that, I want to define something more. I want to do something slightly more general. Okay, so here's what I want to do. I want to have the notion of an F algebra for a functor F on some category. Okay, so a NAT algebra is a 1 plus blank algebra in this general thing. In other words, you look at F, let's call it F nat. F nat of X is by definition 1 plus X. So an F algebra is an alpha from F of A to A. That's what an F algebra is. Okay? That's the definition. And a morphism of F algebras for any F is a mapping beta. Well, give me any other F algebra, beta. Then it consists of a mapping H. This is a homomorphism. And this is F of H. So everything I've done here. So this is the functorial action. So sometimes people write F0 for what the functor does on objects and F1 for what the functor does on maps. The 0 cells and the 1 cell. One will eventually do this in the higher dimensional setting, but let's walk before we run. So this is an ordinary categories and stuff, and we don't have higher dimensional structure, or I'm glossing over issues of higher dimensional structure by waving my hands about equalities. That's where I'm cheating, so to speak, in this lecture in order to give you the ideas. Okay, so in ordinary categories, so that's the notion of what is an F algebra. And so, of course, we have the notion of what is an initial F algebra. An initial F algebra is an F algebra, let's call it iota or I, that has a unique map to every other F algebra. And this will be F of bang. I wrote it backward from the way I wrote it over there, but it doesn't matter. There's a unique homomorphism to every other algebra. So that's what it means to be an initial algebra. Okay. So it has to be a functor. And this is why, for example, in Haskell, it's a completely erroneous to refer to recursive types as algebraic data types. That's completely nonsense because they're not algebras, because they're not, the F's in question are not functors. Okay? This is like caused by imitating the form without the content. Okay, so by the way. So in other words, something like f of x equals x arrow x is not a functor because it's not covariant. It doesn't preserve maps. So it's not even in the game. Okay? So this is the notion of F algebra. And by the way, you can work out for yourself what is an F coalgebra is defined dually. And then we can talk about final, as opposed to initial, coalgebras. So an F coalgebra goes the other way. A to F of A. I'll call it alpha for lack of imagination. And if you have a final one, oh damn, I shouldn't have called it F. Uh-oh, now I'm in trouble. Anybody have a suggestion of what to call the final one? I would have called it F, except that I screwed myself. I need to call it something else. We'll call it J for lack of imagination. So a final coalgebra will be like F that goes from here to F of J. Okay, and what does it mean? It means you have a unique map to it. Okay, such that this diagram commutes. This is F of bang. And this thing is called the co-recursor. And here's a question for you. Does 1 plus blank have a final coalgebra in type theory? And if you wanted it to have a final coalgebra, what would you do to type theory to make that come true? What would it look like? What would be the final coalgebra for FNAT? You should think about that. Okay, it's a nice little exercise to think about. Okay, so now I want to look at Lambek's lemma. Okay, so what is Lambek's lemma? So the initial algebras are defined to be initial objects in the categories of algebras. Okay? But somehow the idea about initial algebras is you want to think of them as solutions to domain equations. That is, I want to think of an initial algebra as specifying a type uniquely up to isomorphism. That's what I would like to be able to do. So Lambek's lemma is the thing that tells you this fact. The Lambek's lemma says the structure map of an initial algebra is an isomorphism. So it says if, let's call it I, from f of I to I, is an initial algebra then I is an isomorphism. In other words, f of I is isomorphic to I. Again, I'm working in ordinary category theory here, and I'm slightly glossing over issues of equality, because when I say that something is an isomorphism, I mean that it has a less than right inverse, which is when composed, are the identity, well, up to higher homotopy if I were working in a higher dimensional setting. But to give motivations, I'm like pretending that I'm working more standard, like I'm glossing over that, which is the standard thing to do. This is why people really prefer infinity categories these days, because they got sick of glossing over these issues of equality and try to embrace them. And when you do that, you get infinite dimensional category theory. So that's like a very nice thing. Okay, so this is what but let's do like textbook kind of thing. So this is the interesting thing. So this is a cute argument. Now watch me screw it up. Okay, so what we have is I have to remember where all the pictures go. Okay, so I think it goes like this. Yeah, oh no, I have to start lower than that. Okay, so I start like this because I have I, which is an initial algebra. Okay, that's what I start with. Yes, because the assumption is I've got an initial algebra. So I want to exploit its initiality. So there's another, just by knowing that, I can name another F algebra. Can you tell me what it might be? Based only on what I've got on the board, what other F algebra exists? You don't know anything about F, apart from the fact that it's a functor. So you should be able to generate for me another F algebra. What is it? Someone?
F of I.
F of I. Right? Because functors preserve maps. So I have another F algebra. Right? Because it's F of whatever to whatever, and a mapping there. So I have another F algebra. So that's an F algebra too. This one is by assumption, and it's initial. Oh, it's initial. Because it's initial, there's a unique map that goes here. Okay, so this is F of bang. Okay. Oh, I drew my diagram 90 degrees rotated, and if I I have the proof all written out. I drew the diagram 90 degrees rotated, so something isn't quite working for me here. What do I want to do here? Oh, that statement is quite right. That is what I wanted. But what am I missing? So I do that, and I have that, and I have that, and then this is that, and this is that. So what I want, before I get that, I'm one step ahead of myself. This F of I, this goes here. Uh-oh, I knew I was going to mess this up. One moment.
I think you're fine, but then
No.
you want to send F of I at the bottom right over to I. But
I want to do what's right. I messed this up. I wrote my diagram 90 degrees out. So I have F of I is that. Okay. And then I wrote this. So that's correct. I knew I wanted that. Then I have F of I to I, which is I. And then I have F of I here. And I have F of I. And then somehow I have F of I to I. I take I think I messed up. So this part is right. Oh, okay. This is not what I want. Okay. So this part is right. This part is right. Okay, good. So I don't want to use the initiality yet. Is the point? That's what I don't want to do. Okay. So I want to claim that I have F of I there. So for some reason, what am I doing wrong? Okay, let me do it how I have in my notes, and then I'll remember how it works. So, excuse me for writing it like that. I will, excuse me for that. Let me just copy it from my notes. I thought I could just rederive it, and now I've gotten myself confused. So, we have the initial algebra. We have another algebra. That part I'm quite right about. Now, I'm not going to use initiality. Okay, that's the point. So first of all, I have another algebra. This map can be copied over here. Okay? And then I can use the functor and put this map over here. I got confused because I wrote it 90 degrees, and then last night when I wrote out my notes, and so I got myself confused. So first of all, this diagram commutes. Obviously, it's f of I followed by I, f of I followed by I. Okay? Sorry. Okay. That's where I got confused. Okay. Now, okay, let's write the initial algebra up here. See, the rotating it 90 degrees confused me. So for whatever reason, last night I was writing the algebras horizontally. Okay, so f of I to I is the initial algebra that we have in question, so we can write that. But it's initial, and this is another f algebra. This is where I was going before. Okay, so what does that mean? That means that there's a map here, bang, and this will be f of bang. That's by initiality. This is by triviality, okay? All right, this is just trivial. But I have an F algebra, so this is an F algebra. And here's the initial F algebra written again. So by initiality is a unique homomorphism to it. So we have I to F of I, okay? Such that this diagram commutes, right? So it commutes by virtue of initiality. Okay. So if this diagram commutes and this diagram commutes, then this diagram, the outer rectangle, commutes. Okay, yeah, that's the important point. Okay, right? This commutes, so the whole, if you go over here and over here, that's the same as over here and over here. Yes? So now what? So now I have a mapping from an F algebra, an initial F algebra, to some other F algebra, which is also initial. Okay? So there's a unique homomorphism from here to any other F algebra, including to itself. One particular homomorphism from I to itself is the identity. Right? So this map, because this map, so that tells us then, since this map, bang followed by I, so I after bang, has to be equal to the identity because there's a unique map, a unique homomorphism from the top to the bottom, and the identity is one of them, and it's the only one. So this map, I after bang, is the same as the identity. So we have that. Okay, so that's the first fact. So now I want to show that, now I want to show the opposite condition. So we have that. Okay? And now, if you look at bang after I is the same as f of I after f of bang, because bang after I is, by the commutation here, f of bang, f of I after f of bang, like that. But now it's a functor, so it preserves the composition, so that's f of I after bang, which I just got through telling you is the identity. So that's f of the identity, okay? And that is the identity, because functors preserve the identity. Good, yeah, so now I did it right. Sorry about once I started out by rotating it 90 degrees, I got confused. Okay, so that's what we do. And that's it. So the main idea is that you just build up this other F algebra, take a unique map to it. See, this diagram is this, that induces a morphism, a homomorphism from that algebra to itself. But there's a unique one because it's initial, so it's the identity. And then you just calculate, chase the diagram. This has to be the identity, and therefore this followed by this is this followed by that, which is the composition that's written here. So this is also this, that, which is f of identity, which is identity. because f is a functor. Okay, and you're done. Okay, so that's the argument. So that tells us that, all right, so this finishes here, is that one reason the initial algebra is interesting is it provides a solution to a domain equation, or a type equation. F of x is equal to x. It provides a fixed point for f. So this is a fixed point. Please, fixed point, 2 words. All right, like that. And if you do a final coalgebra, you can show the same. There's the Coe-Lambeck lemma, which was invented by Joachim Coe-Lambeck, says the exact opposite. It says the exact same thing. It says if you have a final coalgebra, it also is an isomorphism. So it gives you another thing. So you will have, in this setting, you'll be able to show by the Coe-Lambeck lemma that f of j is isomorphic to j. So do that as an exercise. Indeed, the structure map of the final coalgebra is the isomorphism in question. Okay? So the initial algebra and the final coalgebra are 2 ways of inducing a universal or a fixed point, a universal, are 2 universal algebras, universal and co-universal technically, okay? And such things are unique, okay, that they're determined uniquely up to isomorphism. So that's the reason why we care about, I mean, one reason to care about the initiality is I was sort of showing you how the rules for type theory arise from these diagrams. And then this is telling us that it gives us a solution to a type equation. Okay, so then the last thing, I don't have time to do it today, I'll pick it up next time, is I want to show that from this property, I can then prove an induction principle, okay, for natural numbers. I'll do it first for natural numbers, and then I can do it for any F algebra. There's an F induction for any F algebra, and I'll show you how that induction principle works. So then that will give you the heart of what's going on with the dependent type theory and how that works. And then I will put on the afterburners, and I will generalize all of this to something called the W type, which is the type of well-founded trees. And it's basically a constructive version of the ordinals. And then what I will do is I'll give you a constructive version of the ordinals, and then I will then say any inductive type can be thought of as an initial algebra for a polymorphic functor. Not polymorphic, polynomial functor is what I meant to say. A polynomial functor, and the W types are the things that give rise to such initial algebras, and that's what gives you a broad class of inductive types, okay, by reducing it to basically a form of the ordinals. Okay, so what are constructive ordinals? Well, classically ordinals are linear orderings, but that's a kludge. There's no reason to put things in linear order. So what they are is they're well-founded trees. Okay, they can branch infinitely. You can have as many branches as you like. You can go completely crazy with the branch factor, but every branch terminates. There's no infinite branches. It goes like that. Okay, so those are the well-founded. Those are the what are called the Brouwer ordinals. These are the constructive version of the ordinals. So they're not linearly ordered, but they're well-founded preorders. Okay, and how do you say that something is well-founded? Well, unfortunately, in the classical way, you say, oh, there are no infinite branches. That's terrible, no infinite branches. That isn't what you want to say at all. That's like a cockamamie way to say it. If it's constructive, what you do is you say, what it means to be well-founded is that the principle of transfinite induction is valid. That's the correct way to say what it means for this to be well-founded. Not no infinite. That's like a double negation, right? Okay, so we don't want to have no infinite branches. We want to say something positive. The principle of transfinite induction is valid. So we'll come back to that next time, but I didn't quite get as far as I needed to, but I will pick up next time. Okay, thanks.